Hey, so I've been thinking about the past iterations of my reinforcement learning agent, and I came across one of the comments in a past video of one of the viewers saying that the open, high, low, close, volume, data set, as well as technical indicators aren't always the best features to predict either price movement or price change. So I thought I would do a video on ways that we can determine what features are actually important to our predictive analysis, and then seeing if we drop some of the lesser features to into our agent, whether or not that would help. So I just put together this quick notebook to explain that process. Just up front, I know some of you with more experience are probably going to find some holes in this, but if you're trying to determine in any setting a data set in which the features, let's say you have many, many features, and you're trying to narrow down the ones that are most important to your prediction model, this is probably a good way to determine like what those features are. So in the first cell here, I'm going to use the FinRL package because I really like the Yahoo downloader. I really like the feature engineer. And later we can do data split if we want. And it comes with indicators in the Dow 30, which is what I've been testing all my models on. Something for a future video is not using the Dow 30 and using the S&P 500 or something along those lines. And then, of course, the usual suspects, NumPy, Pandas, and Matplotlib as well. So let's go ahead and get those guys installed here. I'm running this on my Paperspace machine. In a previous video, I showed you how to get that set up so that you can use FinRL. You don't have to install it on a Colab each time. It makes working on projects a lot faster. And then I'm grabbing about 10 years worth of data. Since this is an example for just this process, it doesn't really matter what the dates are, but I've just put it for about 10 years or so. And then pass that through our Yahoo downloader to get the data frame. And you can see here it's going to download the Dow 30, which is just 30 tickers in the Dow Jones at the moment. So our current shape is about 86,000 rows and 8 features. I want to go ahead and sort those values by the date and the tick symbol. So you can see here we have about 30 rows for each day representing Apple, right, and Bank of America, Caterpillar, etc. Right. So this wouldn't be this isn't enough features to run a features importance analysis on. So I'm going to go ahead and run the features engineer as well, considering we use this to pass through our reinforcement learning model. And that's just going to add technical indicators. It's going to create a turbulence index. I still haven't played around with this user-defined feature, but I'm assuming that you can define your own features here, pass it through here, and the feature engineer will go ahead and merge your other features into the one data set called processed, right? It makes a copy of that and fills in the non-attributable values. If you think about it, it will create a return. It will create some technical indicators that require a few days of data within the data set. And so it'll just fill those in with 0 instead of having an NA there. So you can see it's successfully done that. And I also want to create a column called increase decrease, which just says if the previous volume metric is greater than the current volume metric, we're going to denote that by a 1. Otherwise, it's just going to remain a 0. So anytime it's gone down, we're going to label that as 1. And I'm also going to create a returns column, and we're going to just define that as the percentage change of close. I wish that the data set had adjusted close. I think in just the regular Yahoo downloader or Yahoo Finance, it does come with adjusted close. I might be wrong on that. It's been a while since I've used it, but I digress. I'm just going to go ahead and create those. And maybe I should show you what it looked well from here. Yeah, actually, let me just show you what processed looks like now. And I'm just going to, whoops, dot sample 5. So I've just grabbed 5 rows at random here, and you can see that we have date, open, high, low, close, volume, tick, day. We have our technical indicators here: MACD, upper Bollinger Band, lower Bollinger Band, RSI 30, CCI 30, DX 30, 30 moving average, 60 moving average. The turbulence index, our defined feature of increase or decrease, noted by one or a 0, and then the returns on that as well. So now we have quite more features in our data set, and we could pass this through our reinforcement learning agent. But before we do that, we want to determine like what features here are actually going to help us with our analysis. But before we do that, we just want to make sure which one of these columns here actually help with our analysis, and if there are any here that we can just drop. So before we do that, the features importance only works on integer columns. So you can see here with the tick data, it's a string. So one thing we can do is encode that, and we can just use that by using the sklearn preprocessing label encoder, pass through that column, and we will see here if I call processed again, it's assigned integer values for each stock. All right, now I know that the tick data, one could argue that the tick data column doesn't have any bearing on the predictive nature of our analysis here. But I think there is an argument to leave it in the analysis because there might be an instance where the stocks might have some sort of correlation with one another, and there might be a way to see that if one stock is going up or if there's, differences of volume between different stocks that are somewhat related by industry, that the agent or the model could gain some insight on that to predict as a whole whether or not the data set is going to go up. So one reason you would perform a feature analysis and try to determine which features are important is because in this instance, it's not very extreme, but there are some data sets out there where you'll have maybe hundreds of features. Maybe you have 30 features. And what that does is, as I guess the idea is when you're first learning, the idea is the more data, the better, because it means there's more information that your model can use to make a prediction. But if you think about it, this is if we take the shape of our data set here, we're talking about 85,000 rows, more than 85,000 rows with 19 dimensions to it. So try to imagine a shape with 19 dimensions to it, and then calculating a certain angle or a certain way that shape is going to perform. It's hard to imagine conceptually, right? Because we can really only think in 4D, which is up, down, side to side, forward and back, and the fourth dimension would be time, right? But then that's the dimension that we live in. So if you can imagine a 19-dimensional space that we need to predict movement in, that's going to be really difficult. So there is sort of this inverse familiarity or this inverse phenomenon with the more features that you have, sometimes the more difficult or the less accurate your prediction is going to be. So you would run this in order to find what features actually have an impact toward your predictive analysis. And we can break that down into two ways in this instance. The first being regression. So regression is just a continuous way of determining one point with another. So in this instance, what we're going to be trying to do is predict the closed value of our data set. The closed value is this guy over here, right? We could pick maybe something else like the open or the high-low. This is why I wish I had the adjusted close, because typically I would just try to predict the adjusted close. And the idea here is that we're going to try to figure out of what features here help us determine the value of our adjusted close. And you can think of it on a line of an XY axis. So one thing we need to do is split up our data and define what features go into what. So X is going to be all the features but the one we're trying to predict, which is our Y. And we need to fill in the NA again, because if we take a look at our returns data here, you split it up into X and Y, you'll have a 0 for some of these, and you just need to fill them in with an NA. And we can then fit our regression model to our data features of our data set. It takes a few moments here. Oh, and if you don't have a 0, for instance, and you have an NA, you're going to get this stack trace example here that says input X contains a non-value. So it's funny, I thought I hit that, but I didn't. So let's try that again. So I just filled in all the zeros with NA, and I've already looked at X. It's typically like the returns here has a 0, and some of these other metrics might have zeros because it takes like 30 days to calculate the CCI, right? Or it might take 30 days to get the moving average. So you'll have some values that are 0, and that's fine. You just want them to represent 0 instead of a non-value. So then once we have it fit, all we really need to do, sklearn comes with the features importance already built into it. So we can just call a variable called importances and extract the feature importances to that variable. And the way to plot this is to take our indexes from this importance variable, get the names from our process data, and then we'll set the X and Y axes given our importances of the indices, and then we'll also put our names as the X ticks. So I know this is a little difficult, but really we're just making sure that we need the indices to actually represent the values, and we need the names so that we know what features we're actually looking at in our plot. If you're wondering what this does here, because I'm in a remote, because I've SSH'd into a remote server, I just need this as part of Matplotlib to show the graph. So let me call this real quick. And okay, so for our regression model, pretty interestingly, the close 30 simple moving average is by far the clearest feature that helps us predict the next value of our close. And that makes 100% sense, right? Like if we have a feature that measures the moving average of our closing price across a 30-day period, it's likely that that movement or that momentum on that regression line there of those values is going to stay consistent. And so we can use that feature to predict our next day's close. Okay, so that's really what this is saying here, as well as the open, as well as the lower Bollinger Band also makes sense. The lower Bollinger Band, you can think of it as, I forget exactly what the calculation is there, but it's a way to help us see the, I think, volume movement or the average movement of price. And typically they're used to show like if you fall below that Bollinger Band, there might be a pricing signal to enter a buy, or vice versa. If it's above the Bollinger Band, there might be a price action to sell. So we can use basically the closing 30, the open, Bollinger Band, lower, high, and then Bollinger Band upper to predict our next day's close. And we really wouldn't need any of this other stuff, like the MACD, the closing 60, the date. I mean, the date, I shouldn't have even put that in there because the date is like whatever. But the volume, which might seem kind of surprising because the volume is probably a very important feature. So, but if we were just doing our regression analysis and trying to predict our close for the next day, then really the only features that would be important to us is this, and all these other features could be actually confusing our model. Possibly, right? This is all just a way to help us think about our data set, right? So one thing about this, though, is that our learning agent likely isn't trying to predict the next day's closing price. And there's really no reason for it to do that. Really what you're interested in is whether or not the price would go up or if the price would go down. And one feature that does, which is interesting, is it's not on this graph here, but one of the features that we've defined in that is the increase or decrease. So one thing that we could try to predict is whether or not the volume of our ticker will go up or if it'll go down, and for a given stock, right? So the way we've defined this is as a 1 or a 0. And so really what we want to do is run a classification on our features to determine what helps us predict whether or not that stock will go up or down in terms of volume. So we can set up it the exact same way, but instead of a random forest regressor, we'll call a random forest classifier, which I've defined down here. We've again just processed our X and Y with all the other features in our set besides the increase decrease. So let's go ahead and instantiate our variables here. We'll call the classifier and we'll fit it to our model. And it just takes a few moments. Again, we'll instantiate the importances with our model's feature, and we're essentially calling the exact same plot, just with the newly instantiated features of our model. And here we get a totally different picture. So the close is still our most important feature to help predict that increase or decrease. But the ticker also has a really high importance on whether or not we can predict an up or a down in an increase or decrease of volume. And then, interestingly, third, the increase or decrease is based on the volume of our data set, yet it comes in third for importance on predicting that up or down. So basically, our classification model has decided that the close and the actual symbol, stock symbol, play more importantly to predicting an up or down than the actual volume itself. And then in decrease, it's the high open, the date, the close 60, Bollinger Bands, right? And then we get into our technical indicators. The day is the least important here. So one could think, well, maybe I'll drop the last, 1, 2, 3, 4, 5, 6. Maybe I'll drop the last 6 features, or maybe I'll just take the top 3 and then the second top 4, and I'll cut the other features here. And we should have enough, predictive importance in our features here to have a good predictive model. And I'm actually leaning toward this classification method. I'm not really interested in a model that can predict the next closing price. I really just want a model that's good in predicting whether or not something is going to go up or down in the mid to near future, because that's really what you're going to be pricing that's really how you're going to be basing your buy and sell positions, is based on the actual future movement of the symbol itself. Again, I'm sure you could find holes in this. It's not like I've done a ton of robust data engineering here. I really just passed through a very simple data set, but this is something to build off on because this is something I've been thinking about a lot lately. And then lastly, I wanted to throw this in here is correlation. In some instances, if you have really highly correlated features, you could be biasing your model toward those features that are highly correlated, or you might just get so much overlap in those features in your analysis that they're really you really don't have a set of features that individually as columns, as features themselves, actually help perform a prediction. And so you're really just having lots of features in there for no reason when you could get the same predictive force from just having one of those columns in there. So it's good to know your correlation of features as a way to understand your data set as well. So let's just go ahead and call a heat map here. I really like heat maps. You can get it through Seaborn. We just create a variable called correlation, and that's the correlation of our processed features here. That's what the core does. And then we create a method called heat map. And I've called purples, but there's tons of different colors here. And then I've just defined the ticks here. And let's go ahead and show you that. Looks like something's getting deprecated here. And then this big plot here is what we have. So because we have so many features, it's kind of hard to show you all in one go. The darker the purple, the more highly correlated they are. So for example, let's take this big square here. So for the open, it's highly correlated to down here, which is open, which makes sense. So all the features in the diagonal path here are a 1-to-1 correlation because they're the same feature. So the second one here is correlated to high. So open, high, and low are all highly correlated to each other, almost a 1-to-1. It's the only close that isn't a 1-to-1 correlation with the others. So interestingly, one could argue that the open, high, low is really just representing all of the same correlated importance in terms of features. So do you really need all three of these, or do you really just need one of these columns? Because if you have one, likely whatever predictive force or predictive capabilities that feature has, the other two also have, right? So you really just need to choose one, unless you were trying to predict something else, right? It seems like open is also really highly correlated with the upper Bollinger Band as well as the lower Bollinger Band. And that makes sense because a lot of the technical indicators are calculated based off the open, high, low, right? Obviously, the upper Bollinger Band is going to be highly correlated to the lower Bollinger Band. And they're going to be highly correlated to the open, high, low because those are the features that are used to calculate this feature. Same with close 30. Looks like those are really highly correlated with open, high, low close and the close 60. So yeah, and as well as the other, looks like the other Bollinger Bands are really highly correlated to the close 30 as well. So this heat map is a really good way to determine like, okay, I've thrown in all these technical indicators here, but do these technical indicators say the same thing about my data set? Do they actually provide a unique uncorrelated value that we could use to help predict our feature here? So yeah, just something to think about. This is a really easy notebook, and I hope you guys enjoyed this. I'm going to try to use my findings here, or whatever insights that I've gained from this, to pass through a new data set into hopefully an ensemble model to see if we can get some better results. I feel like we're getting better and better each day. So stay tuned, and I'll see you in the next video. Bye, everyone.